Alright, so there was a change of plans, so I'm not going to talk about Elixir anymore. That's boring. I'm going to talk about property-based testing instead, which is much more fun, and it works with many more languages than Elixir does, being a language. So my name is Andrea, that's my handle on the internet. I'm a member of the Elixir core team. Elixir is a programming language built on top of Erlang, which is another programming language. And it's pretty young, it's like 5-6 years old. It's functional programming language built for building distributed, concurrent, fault-tolerant, reliable systems and resilient systems. I work at a company called Weedmaps. Has anyone heard of this company? No. Has anyone ever heard about wheat? As in like the stuff that you... Yeah. So have you heard about Yelp? Restaurants. So Weedmaps is like Yelp for weed, so you can like find dispensaries that sell weed legally, of course, and you can like review the dispensaries. You can review different kinds of weed. Maybe some kinds get too higher, I don't know. So I work in Italy, so none of this is legal in Italy, so I don't use this ever. But that's what we do. If you're interested in weed, we are hiring. Disclaimer: there's no weed consumption included in the job, it's just programming. But if you go work in California, where the HQ is located, then there's weed consumption. I mean, at your discretion, but you can consume weed at home. Yeah, that's it. So we're going to talk about testing today, sadly not about weed. Let's talk about testing. So why do we test? We test because if there are no tests, then we are not confident in our system. We are not confident in making changes to our system because we don't have an automated way of checking if our changes break stuff. So we don't have coverage of our system with automated testing. So we're not confident in doing anything. We're not confident that our system works and in changing it. If we have tests, we're kind of relieved. That's what a BMO says, because we are more confident that if we do changes and run tests, and the tests pass, then our system is still working. And if the tests pass, our system is working. That's the assumption. So we are free to make changes, and we have more confidence in our system and in changing it. The probably most common way of running tests and the most foundational way of running tests is unit tests. Unit tests look something like this. This is Elixir code, but it translates to many, many languages into something very similar to this. So here we have a test that's testing a sorting function that sorts lists of integers. So in this test, we're saying, okay, if you sort the empty list, it's still an empty list. If you sort the sorted list, it's still a sorted list. If you sort an unsorted list, it becomes a sorted list. So it's really straightforward. You can consider this, you can kind of think about this kind of testing as example-based testing, because you have a bunch of examples that you know the way that they should work, and then you just assert that they work that way. So you know that, for example, the sorting 2, 1, 3 should end up in 1, 2, 3. You know this. So you basically give a bunch of examples of how your code should work. And then the program just verifies that these examples are true. Another way to think about this is table-based testing, where you have basically a bunch of inputs that you know how your code should handle, and a bunch of respective outputs for those inputs. And then the unit test goes over each input and verifies that it matches the output that you expect, in a table-based fashion. Unit tests, they're good for a lot of things. So, for example, they're very good at testing known corner cases, like the empty list in the example. We know the empty list is kind of a corner case for lists, because it's a weird list. So we can test it directly, and we can directly decide what our program, and test what our program should do with the corner case. It's very good at testing regressions as well. Unit tests are very good at testing regressions. So if you have a bug that you find out, then you can write a unit test that reproduces that bug, and you can fix that bug, and the unit test can ensure that the bug never pops out again. However, unit tests they have a bunch of downsides as well. First one is that you're always testing the same inputs, so you're never finding about inputs that you don't know about that would cause your program to break. And also, writing unit tests, it's really hard to express properties of your code. So in our example for sorting lists, it was a simple example, so it was easy-ish to understand what the function was doing. But for more complex examples, it's really hard to tell what your code is supposed to do for every possible input just by giving a few examples, right? So if we forgot to add, for example, the empty list case, we wouldn't know how our code would behave for the empty list jump just by looking at tests. So these are unit tests. So properties kind of fix some of the downsides that unit tests have. So properties are definitely harder to write than unit tests. You have to reason more about them, but they can make testing much more, they can make the testing of your system much more robust and deep. So basically how property-based testing works is you define a bunch of valid inputs that your code can handle, and you don't define specific inputs, you just define the shape of the inputs. So for example, in the previous example, we would have lists of integers. So the sort function would have to handle all lists of integers, period. You just define the shape of the inputs. Then you define a bunch of properties of the output, so how your code should behave. So properties that hold for whatever input that follows that shape is fed to your code. So if you give a list of integers to our sorting functions, then the result should have some properties that are true regardless of the input that you give to the function. And then you take this shape of valid inputs and these properties of the output and you feed them to a testing framework. And the testing framework is responsible for generating a bunch of random inputs that are in the shape of the valid inputs that we have here. It generates them at random, and it generates a lot of them, and it feeds them to your code, and then it takes the output and it checks that the properties that you specified hold for each output that you generated, that the code generated. So it's the responsibility of the testing framework to basically try to break your system by generating inputs that you said are valid, but that actually break your system. So in this talk, I will use Elixir for examples, but it doesn't matter because it's pretty much the same in every language that's property-based testing. I will use this library over here, which is written in Elixir for examples as well. This doesn't matter either because the principle is the same for every property-based testing framework that I know of, so it doesn't really matter. So let's see an example. We saw how we would test sorting lists with unit tests. So let's have a look at how we would write the same with properties. So how we would write properties for the sort function that we saw earlier. So this was the unit test that we had, where we tested the empty list, the sorted list, and then unsorted list. So there's just 3 inputs. So the first thing that we have to do to write properties for this is find out the valid inputs for this. And as we already said, the valid inputs for the sort functions are just lists of integers, right? So that's the shape of our valid inputs. Now we have to, and then it's the responsibility of the property-based testing framework to generate random lists of integers. We don't care. We just care that the valid inputs are lists of integers. And then we need to think about properties. This is a really hard part, is to think about properties that your code has, that the output of your code has, if given a valid input. So for sorting lists, the properties of the output of the sort function could be that the output is a list. So the output of sorting a list should still be a list, regardless of the input list. It should have the same elements as the input list. So if you have a list and you sort it, you don't lose or add any element, you just reorder them. And then it should be ordered, right? So this is something that we can actually check for any list if it's ordered. And basically we would, the property of sorting is that every sorted list is ordered regardless of which list you order. This is how it could look like in using stream data, which is again, it's a specific library, but it would look something like this in any language or property-based testing library you would have. And so in this example, first of all, we define the inputs. So we define the shape of the inputs. We have a list of integers, which is a generator that represents the shape of the input, which are a list of integers. We bind that to the list variable so that we can use it in the body of the test. Then in the body of the test, which is in between do and end, that you can see it here. We sort the list first, and we have a sorted list now, and then we assert the properties that we mentioned earlier. So we assert that the sorted list is still a list, we assert that it has the same elements as the original list, and we assert that it's sorted. So it's not important what same elements in order are, what they look like, but the principle is that we test those properties. This is the whole property test for this, right? So if we were to write unit test and do test-driven development, we could start with a function like this to see how it breaks. So this function, it sorts the list by just returning the list. So it's clearly broken, at least for 2 out of 3 properties, right? Because it's the output is a list and it has the same elements, but it's the same list, but it's not ordered, so it's broken. So this is broken, but the property-based testing framework just generates a bunch of random lists of integers. So this could be a list of integers that it generates, right? It's random, it's just a bunch of integers in a random order. And this list definitely breaks this implementation, right? So if you pass this list, it just returned as is, and it fails the property of being ordered. The problem is that by looking at this list, it's not super easy to tell that this list is not ordered. Or, I mean, it's easy in this example because the example is trivial, but with a very complex generated input, it could be a very noisy input. It could be very hard to tell what property it has. So what pretty much every property-based testing framework does is they shrink this input to a minimal input, to a smaller input that still makes the test fail. So in this example, you will never see this is the input that actually caused the failure originally. You would see something like this. So the property-based testing framework would shrink that list and would say, okay, what's the simplest possible list of integers that will still make the function, that will still break the function, the implementation that just doesn't sort the list. And this is much easier to understand because it's just a list of small integers with a minimal number of integers in order to break the implementation that we have. So it's just 1 and 0, and it's easy to tell that this is broken because they're not ordered. The integers are small, but this is small and it's much easier to understand. So this is how property-based testing works. Now I would like to talk about mostly 3 things, which are 4 things, let's say, which are generators. So just quickly go over generators and how they work. And I want to talk about a bunch of patterns to use when writing properties, because the hardest part of writing property-based testing is coming up with properties. So there's a bunch of patterns that you can use to make that part easier. Then I want to talk about stateful testing, and then I want to talk about what plans we have at least for Elixir for the future. So generators, really quickly, they are what is used to define the shape of the inputs that your code can take. So, for example, we have a bunch of, in this stream data library, we provide a bunch of generators, like integer. So integer is a very basic generator, it just generates integers. And if you take, it's an infinite stream of integers, so it can generate as many integers as you want. If you take a bunch of integers, like 4, it will generate a list of 4 integers. And they kind of duplicate because it doesn't matter that they're unique, and it just returns a bunch of integers. Generators themselves are useful, but the most useful thing about generators here is composability, so it's composing generators. So how do you create generators for your custom generators? How do you create generators that work with your program or that generate particular inputs that work with your program? And that's by composing other generators. So the library provides a bunch of basic generators like integer that return, for example, basic data types, and then it provides a bunch of ways to compose the generators. So for example, if we want to have a number generator that generates either integers or floats, the library provides integer, which is a generator that generates integers. It provides float, which is the same thing for floats, and then it provides this one-off kind of composition function, which takes a bunch of generators and generates terms from one of those generators at random. So in this case, we'll generate sometimes an integer, sometimes a float at random, and then each integer and each float would be random as well. You have other functions to, for example, map a function over each generated value. So this stream data will map. In this case, this one is a generator, for example, generates positive integers. So it takes an integer generator, which generates any kind of integers, negative, 0, or positive, and then it maps the absolute value function over them, so that in each integer you're sure it's positive. And these composition functions are really useful because they let you create any generators that you want, pretty much, and they retain shrinking properties. So, for example, in this example, if you generate a positive integer through this generator, then when you shrink it, the shrunk integer will also be positive. You wouldn't go to a negative integer when shrinking, which is really good. And just as a quick example, this is how we actually use these composition functions in our in stream data in the library to create any kind of generator. So, for example, we have a generator that generates ASCII strings, and that generator is just a matter of choosing a random, so taking the generator that generates each random ASCII byte, then making a list of these bytes, and then mapping list to string so that the list actually is converted to a string. It's just to show that we use this composition stuff a lot internally to create any kind of generator. So generators are just like, they're really important, but they're kind of simple to understand. They just generate values, and they're used to define the shape of the inputs. A much harder part when doing property-based testing is thinking about the properties that your code could have. So I want to just talk about a bunch of patterns that you can try to recognize when running property-based tests, and that can help you write properties. So the first pattern is circular code. This is really easy to spot and really easy to understand, and super easy to test with property-based testing. So circular code, what I mean is when you have some code that looks like this, so you have some encoding code that takes something and encodes it in some way, and then you have the opposite function basically, which is the code, which decodes the encoded term and goes back to the original term. So it's kind of a circular code. You can keep encoding and decoding, and you'll still go always back to the original code. And this is really easy to test because you just generate any random term and assert this. This is the assertion that you have. And an actual practical example I have is from a JSON library that we have in Elixir called JSON, JASON, and this is an actual test that is in the code base for JSON, which is about Unicode escaping. So they have an encode function for strings that escapes Unicode, and they have a decode function that is supposed to decode the escaped Unicode. And this test basically ensures that whatever string you generate, then you can encode it with Unicode escaping, and then you can decode it and you'll go back to the original string. It's actually found bug, a couple bugs I think in the library, so it was really useful to have. Another pattern that I want to talk about is the Oracle model. This is a really useful pattern as well, and a really easy to spot as well. So whenever you have some code that you can consider an Oracle code, so you can consider some code that works, and you're implementing another version of the code in some way, you can basically assert that for any possible input that they take, they behave the same. This is very useful when you have, for example, an older system that you're re-implementing, and the older system works, and you're implementing a new version, and then you can test that for any input, the new version behaves exactly the same as the old version, and we call, in this case, the old system would be the Oracle. Another thing that you can have is a less performant implementation of your code, but that is really easy to understand, so that you're kind of sure that it works, but it's too slow. So you want to implement the faster version, but you can use the slow version as an Oracle, so that you assert that the fast version always behaves like the slow version. And a practical example that I have, I'm running a HTTP2 library in Elixir, client in Elixir, and HTTP2 involves Huffman encoding, and there's an Huffman, the colon Huffman is an Erlang library that does Huffman encoding, and I had to write this implementation in Elixir, and what I did was just, okay, I wrote my implementation, then I'm testing the two implementations behave exactly the same for any kind of input, for any binary input that you have. So this is really useful pattern, the Oracle model. In this case, the Oracle implementation would be the Oracle. Another pattern that there's a link to a YouTube talk where I stole this idea. Probably you can read this, but it will be in the slides. But it's to use property-based testing for doing smoke tests. So, for example, imagine you have an API, HTTP API, that can return one of these 4 codes. It can only return one of these codes, status codes. So what I can do is I don't care about testing the actual output of the API, because that would be very complex to write properties for. But what I can write properties for is just that for the status code of the response. So what I can do is I can generate any random HTTP request at random, and then I can issue the request, and then I can check that the status is in one of the 4 expected statuses. So of course this one will never catch errors like a semantic error where you issue a request that is supposed to return 200, but it returns 404. It wouldn't catch that because we don't know the shape of the request, but it would ensure that your system basically knows how to handle every possible request with one of the expected response codes. So we assert that it doesn't blow up, right? This is a smoke test, so it just asserts that it doesn't blow up, it doesn't return any unexpected error codes. So we're at least checking that that the system behaves in an expected way, not in an unexpected way. Another very small tip that I have, is not a pattern, just more as a tip, is to execute a very small number of property-based tests locally, and then let CI, continuous integration, do a lot more of the testing. So each property that we can run, when we write check call and run property-based tests, it generates a bunch of random inputs, as I mentioned, right? So each property is tested against many generated random inputs. But that many part is configurable. So you can say, okay, use 100 random inputs every time, or use 10 random inputs, or use 1,000 random inputs. So the idea is that it would be good to do not a lot of inputs locally, and let CI generate a lot of inputs. So you would have something like this in your configuration. This is still Elixir specific, but it applies to everything. So you would have, if you're in CI, do like a lot of generate a lot of random data, because you have a lot of time, and it takes time to do these tests, right? But locally, you can generate just a few, because you're going to run the tests locally many more times than you do on CI. So you're still covering a vast input space, but it's just faster, and the feedback loop is faster. The last pattern or tip that I have, I think, is to use properties whenever you can, and they're useful for a lot of cases, but still, unit tests should still be present in your system alongside properties. So unit tests and property-based tests are not exclusive. So this is an example that we have in the Elixir code base, where we have a string contains function that checks if a string is contained in another string. And the property-based test for this just says, okay, generate 2 strings, left and right, at random, whatever strings they are, and then assert that by joining them, so by doing left joined with right, then the result should contain both left and right? So if you join 2 strings, the result should contain both strings. So this is a really useful, it actually got bugs in our implementation or in the design of this function. However, so what happens if you implement string contains as returning always true for any input? This actually still passes, right? Because it's just 2 assertions that assert that string contains is true for whatever, but if string contains is always true, then they always pass. So the idea here is that you would have this property for string contains, but you would also add another test, which is a unit test that actually checks some real-world inputs, right? So we say that string contains, that foo bar contains foo bar contains bar, and foo bar contains OP as well. This should be it's a typo. And so there's another thing missing here that I forgot from the slides, which is that you should actually check that something like Z, the string with Z in it, is not in foo bar. So you would actually assert that this function kind of works for a few inputs, like a few examples that work, but then you have the property as well to check that it works for every possible input. Second to last thing I want to talk about is stateful testing. So what we saw until now is called stateless property-based testing, because we just generate inputs at random, execute the code, and assert on the output. The code that we execute is usually stateless. So it's just functions that take input and return output. Stateful testing is done so that we can use property-based testing on stateful systems, so in systems that hold state. And the idea is based on three main concepts, which are a model, a bunch of commands, and a bunch of assertions to test the system. So the model is just a state that represents parts of the system that we want to test, so that we can do assertions on the model. Then the state transformations, and so the model is a state, and a bunch of state transformations so that we know how to update the state. The commands is just a bunch of codes that we can execute on our system and our model, and a bunch of preconditions so that we always only execute codes that are valid in our current state. And then the assertions are just post conditions that we check after every call, after every comment. So after every comment we say, if after this command this should be true, and that's the actual test. So that's the actual thing that would fail if there's a bug in the system, right? And just a simple example that makes, I think, it much easier to understand this is, say we wanted to test the getting and setting of keys in Redis, right? So Redis is a key value store, we can get and set keys, and we want to test this with property-based testing for stateful systems. So we would have our system, which is the actual Redis instance running, and then we have our model, which could be a map, like a dictionary, so a key value data structure. They behave the same, right? They can only have the keys are unique, and there's one, so the keys are unique, and you can store value at one side of key. So they behave the same, and our model represents the Redis system, basically. And then we can have a bunch of commands, and we could test just getting and setting, right? So we would have a get command that gets a key, and a set command that sets a key to a value. There's like basic Redis commands. So the implementation for these commands for our model would look something like this, where we actually do the same operation of getting and setting on a map, so on a dictionary or key value data structure. So get would just get the key from the key value data structure, which is our model, and set the key in the model. So put the key in the key value data structure. And then we would have a bunch of commands that we can execute in the system. So for example, we would have a get command that gets one of the, so we can have, so we have a model which represents the system. We can get all the keys from the model, which are supposed to be all the keys that we have in Redis. And then we can say, okay, the get command would just get one of those keys at random. The set command would just set a random key to a random value, and then another set command could set an existing key. So one of the existing keys to a random value. So we also test the overriding of keys. And then we would implement the actual commands and post conditions and state updates. So for example, for get, we would actually get the stuff from Redis. So we would send a get command to Redis, we would fetch the stuff from Redis, and we would assert that the result in our model for that key is the same as the result that Redis gave for that key. So this is the actual check that our model is behaving exactly like the system under test, which is Redis. And for example, we would test the setting of an existing key, where we would issue the set command on Redis, and then we would just, so there's no test to do here, except for actually executing the code, and then we would replace the key in the model with the same value. So the property-based testing framework, what it would do now is generate a bunch of commands at random, so like a bunch of gets, a bunch of sets existing, a bunch of sets, and it would just generate a list of commands at random, and it would try to execute them and check the post condition for each command. And at some point, it would find a bug, so a discrepancy between our model and the system, and it would actually do the shrinking part that I mentioned earlier for the commands as well. So it would try to find the minimal sequence of commands that would reproduce the error with the simplest possible inputs to those commands, so that the error is still there, but it's much easier to understand. And while stateless property-based testing, which is what I talked about initially, is very useful for testing simple code or stateless code or kind of pure code, the property-based testing world is very focused on stateful property-based testing, because testing stateful systems is much more, can be much more powerful than testing stateful systems. And one example that I have is LevelDB, which is a key value store from Google, I think. So they use property-based testing, stateful property-based testing for testing this. And when they ran it the first time, they found a sequence of 17 calls to the database, which would cause a ghost key in the database, so it would cause a bug. And that 17 calls, that's a minimal possible input, possible sequence of commands that would cause a bug. So it would have been really hard for a human to find a minimal sequence of 17 calls that would cause the ghost key, right? So they ran this, they found the 17 calls, 17 sequence of 17 calls that would uncover the bug, they fixed the bug, ran it again, this time 33 calls to find the bug to create a ghost key, and that's still the minimal. So there was another minimal list of sequence of commands with 33 commands in it that would still break the system. We fixed that, and now there should be no bugs, hopefully. So this is, I mean, it's really useful because the human would never be able to do this problem. So the last thing that I want to talk about is just some research that we are personally doing in Elixir for property-based testing. So this is more interesting if you're interested in the Elixir part of this. But so one thing that we want to do is integrate dialyzer and stream data, and this would be a Google Summer of Code project for this summer, hopefully. And dialyzer, if you don't know, it's a static type analyzer for Elixir. So in Elixir, you can basically have a bunch of type annotations. So you can define types, and then you can annotate your functions with specs that specify the type of the input value and the type of the return value. And this dialyzer tool runs a compile time, so it's not, runs statically, and it looks at your code and tries to find discrepancy between specs and between return values and everything. And what we want to do in this Summer of Code project, Google Summer of Code project, are two main things. First one is to be able to create generators from type. So we have type annotations like type, my type, which is integer. So we want to be able to turn my type into a generator or turn integer into a generator. So for example, say we have a type like this where it's timeout, which is either the atom infinity or a non-negative integer. We want to have a function or something. The API is not there yet, but we want to have something that takes that type and creates a generator around it. So it creates a generator to generate terms of that type. So in this case, you would probably compile something like this, which is either infinity or a non-negative integer, which was the definition of the type. This is the first step. This is kind of straightforward to do, so we're not too worried about that. The second part is much more interesting, it's much more difficult to do, which is to do automatic property checking of specs. So as I showed earlier, we can spec our functions so that we can say, okay, my function is supposed to take an integer and return a term of my type, so in this case an integer as well. And we want to be able to test that with property-based testing automatically. So we want to have, so say we have something like this, where we have my function that takes a timeout and returns either OK or the atom OK or the atom error. We want to be able to test this automatically, test that this is true, or at least we want to test automatically that we can call my function with any possible timeout and it will still return either OK or error. So it's kind of a small test as well, but it's automatic, so it would be very, very powerful because you don't have to do anything to test it. So this one would compile something like this, where we have from type timeout, so we create the generator from the type, then we take timeout, and then we start calling the function with that timeout, randomly generated timeout is either OK or error. This is very useful. It's a smoke test again, so we're not testing that for that OK or error are returned semantically. So they're correct semantically, because we could return error when OK was supposed to be returned, and the test would still pass, but it asserts that for any given input, in the valid inputs, the output is valid as well. This is a bit more complex because it involves actually checking that something is part of a type, which is not something that we have in Elixir early on, but it's something that we want to work on. So this is all part about automatic property-based testing of specs. It's very similar to something that Clojure has, which is clojure.spec, which is like a way to basically do the same thing. So you can use for property-based testing as well, where you can find what a function should take and what a function should return, and then it's automatic. It tests that automatically and can output. So in conclusion, I want to do some acknowledgements. So the first link, test.check, is a Clojure library where I stole most of the ideas for stream data. So I'm really grateful to the authors of that. Erlang Squeak Check, of course, that's like the main implementation of Squeak Check, which is property-based testing. And it's a very complex implementation, and it's kind of leads the whole property-based testing world. And then the last one is the actual original paper where property-based testing was introduced for Haskell. And then just a couple of resources. So the first link is documentation for stream data, if you're interested in the Elixir part. And the second link is an actual online book about property-based testing. It's in Erlang, but it's still very useful, I think, whatever language you want to use property-based testing in. And then, so just to recap, why property-based testing is useful for finding those obscure bugs, because it generates random input that you wouldn't think about, and that would break your system. Then it's good for reducing this random input to minimal failing input, so it's easier to understand why the input caused the system to fail. It's good to find specification errors, so sometimes you think that your function takes a bunch of values, but then you say, okay, test my function against this bunch of values, and then you find out that the function doesn't work with a subset of those values, but you realize that it's not a bug, it's just that it's not supposed to take these values. So it's easy, it's very powerful at like making you understand your system in a deeper way, at least what inputs and what outputs your system is supposed to take and produce. And then it's very good at covering a vast input space, of course, because every time you generate random inputs, and every time you run this, it's different random inputs, so you cover a lot of inputs, possible inputs for your code, which is good and gives you more confidence in your code. So just a curiosity for Elixir, people that are interested in Elixir, this library will come with Elixir 1.7, so it will be shipped in core Elixir without the stateful testing stuff. But in the meantime, you can use property-based testing for whatever language you're working on, pretty much. So if you're using Elixir, the stream data library, I would recommend. But there's libraries for all these languages, and probably more languages. These languages, I just know for sure that there's libraries. So you can go and use property-based testing, pretty much whatever language you're in, and the whole everything that I mentioned would work pretty much the same way, and the principles would be the same. And that's it. Yeah.
Thank you, Andrew. Questions?
Thank you for the talk. Really nice, amazing friend. I would like to know, because it reminds me a little bit contract by design, from Bertrand Meyer, Eiffel, programming language. What are the different similarities between?
I didn't get the question, sorry. It reminds you of what?
Contract by design.
Contract by design.
Yeah, where you have this precondition, postconditions, and invariants all the time. So property-based reminds me a little bit that way of development. So maybe you can enlighten us with the difference or similarity.
I have never heard about contract by design, so I would need to read about that and then answer. Yeah. Any other questions that I can answer, maybe?
Hi, my question is, how do you test the tests? I mean, it's obviously a very stupid question, but sometimes you have bugs in your test, and your unit tests. Sometimes the way to avoid those bugs is to follow a predictable cycle and write your test as down as you can. So what if you have a bug in your property-based testing and it keeps okay? So is there any technique to handle that?
So this is an inherent problem with testing in general. So how do you ensure that your tests are correct is like a problem that doesn't just relate to probability-based testing, it relates to every kind of testing. With probability-based testing, it's a bit harder because the probability-based tests are harder to write. They're more complex pieces of code, so there's a higher chance that there are bugs in them. The answer is I don't know. I mean, it's hard to ensure that there are no bugs in the tests, but there's no. I mean, you wouldn't test the tests because the tests are testing already. So, I mean, it's with any other kind of tests, you pay more attention. I hope that you don't write bugs in your tests. I wouldn't know how to. Do you have any question that I can actually give a cool answer to, or they can look confident in what?
I have a question. So yes. I think it's awesome that this will be included in the next standard Elixir release.
Yeah.
But you've already been developing. What kind of feedback have you gotten from the community?
community or like people actually using this?
So we got scolded a lot for doing this. People got really angry because there's already a bunch of implementations that work for Erlang and some that work with Elixir. So the feedback has been, some of it has been negative, most of it has been positive. So our idea is that we want to include this in Elixir because it's going to make it easier for people to use it because it just bundles in. We can ensure that this is maintained forever because, I mean, as long as Elixir is maintained, because we're maintaining it, we can ensure that we can use this in Elixir because it has the same license as Elixir has, so we can actually use it to test Elixir's code base, which we couldn't do for using like external libraries. And the idea is that, yeah, I mean, the idea is that we want to promote this a lot, so we want to put it in Elixir so that people use it. Because it's just there. And I mean, honestly, feedback has been really good. People have enjoyed working with this library in particular, so I'm pretty happy about it.
This is great.
First of all, I wanted to know if you have heard of the Haskell library Hedgehog.
The Haskell library what?
Hedgehog, like Sonic the Hedgehog.
No.
I wanted to know what approach did you choose to the shrinking part of the...
Oh, yes, nice.
That's a very
This will make me look cool. Although I stole this approach, so it's not actually my idea, but I guess I found it on GitHub, so that was my part. But so how we do shrinking is that when we generate a value, we don't generate just the value. So say we generate the integer 5, we don't just generate 5, we generate a whole tree of values that is lazy, right? So it's lazy, I mean that only the value 5 is actually there. The rest of the tree is a function that you. So it's a lazy tree where the children of the root are not realized or not executed until you actually shrink. So we generate this tree with the root 5, and we test our code with the number 5. And if it passes, we just throw everything away and generate another value. When there's an error, we take this, for example, say the 5 generates an error, we take 5 and we have this tree where each child is smaller than its parent. So we would have, for example, child, and then the children will be 0, 2, and 4, right? And then we go down and say, okay, does 0 still, so 0 will be the smallest, so does 0 break this? No. And we try 2. Okay, does 2 break this as well? Yes. Then we generate this, the rest of the tree until we find way down the tree where we reach minimal failing input. So say 2 still fails, 1 still fails, but 0 doesn't fail. So we say 1 was the smallest possible value. And this is a really nice idea because it's really easy to understand the tree because it's just a tree where the root is your value and then every child is just a smaller version of your value. It's lazy, so it's really cheap to create because you just create a way to create it. You don't actually create the tree ever, except when walking it down when shrinking. And it's really easy to compose because, for example, when you map a function over a generator so that every generated value has that function applied to it, then we just lazily map that function over the whole tree so that whenever we shrink, we actually shrink, and then when we realize the value in the tree, we actually map the function over it. So it's really easy to compose generators and compose the trees as well. Yes.
Well, that's exactly the approach that Hedgehog takes.
Yeah, and that's the approach that the closure library test.check takes, and the right is called for. Thank you very much.
¿Alguna otra pregunta?
Yeah, I'll leave you with a fun fact. So at Weedmaps in California now we're experimenting with online ordering as well, so you can actually order wheat, get it delivered to your house. So it's gonna be not Yelp for wheat anymore, but Uber Eats for wheat. Yeah. But that will make some people happy.